Welcome, I am Gonzalo, a BCAM intern inside of the linear and nonlinear waves directed by Luis Vega. Before starting, you should know what a neural network is and, more concretely, a physics-informed neural network. For that purpose, I recommend this article from 2018. Both that article and this collab is going to be available right below. Today, I'm going to show how to implement a physics-informed neural network, or PINN for short. To do so, we will use TensorFlow for Python. The aim of this video is to approximate the solution of this heat equation and then train it by setting this loss function. The training consists of minimizing set function with respect to the weights and biases of the neural network. Every sum is responsible of imposing an equality of the problem. This one is responsible of the first one, and the two others are responsible of the initial and boundary conditions. Note that we need to select some points in a domain, which I chose to be this rectangle. Apart from TensorFlow, we will use a few others, like these two, to plot our results. As you can see, I prepared two different implementations. What I call vanilla implementation is a minimalistic approach that exploits a lot of the inbuilt functions provided by TensorFlow keras. The complex implementation, on the other hand, uses way less of keras to allow a better performance and customization. Let's start with the vanilla implementation. PINN Builder creates a keras sequential, just a normal neural network, where each layer has a number of nodes specified by the user. It also adds an scaling layer, so the input is mapped to the squared minus 1 squared, just in order to accelerate learning. Now I define the loss function. Because how the method that trains the neural network works, the loss function needs to know the model and the points to evaluate f. This f. That was the hard part. Now we can continue. These two functions are just plot functions. This section is to randomly select points in a domain. The previously defined function is called to give us a neural network of 3 hidden layers with 100 nodes each. As explained, a minimizer is required. And with this configuration, we achieve better results. Compiling is just to give the optimizer and our loss function. Now we can train, finally, our neural network, and it takes about 5 minutes. Now we can compare our approximation with the real solution. Here our approximation, here the real one, almost identical. Here our approximation, and here the correct, exact initial condition. I too calculated the relative error, and we get something like 0.003. And that's all for the vanilla implementation. Now, let's continue with the complex implementation. This function is the same as before. These two are almost identical to the loss function defined on the previous implementation. the same thing. And here we get something new. Now this new function gives the gradient of the loss function with respect all the weights and biases of the neural network to the optimizer. So this last one can update the variables and therefore get a decreased loss. This function just generates random points on the domain specified. And here we have our last function, the fit function. Just to show what can be done, I made a pretty complex function as a demonstration. If the user wants to, the options of the optimizer are automatically adapted here. This way we avoid tries and errors. It can also select another training data after a number of iterations given by the user. Just as before, plot functions, variables that we are going to use, and here the construction and training of our PINN. Note that we achieve a faster training, 4 minutes lower. Now we can, as before, compare our solution with the approximation. Again, almost identical. Almost identical. And our relative error is 0.008, lower than the previous implementation. That's all. I hope this was useful and see you!